Welcome to The Explainer. Today we're going to take a look at something you've probably done 1,000 times. But have you ever really thought about what's going on? We're going to follow a single water molecule on its incredible journey when you boil a pot of water. And trust me, it's way more fascinating than you might think.
So, yeah, what is really going on in there? I mean, on the surface, it seems super simple, right? You add heat, the water gets hot, and poof, it turns into steam. But what's actually happening at that microscopic molecular level? It turns out this simple, everyday chore holds the key to some of the most fundamental rules of thermodynamics.
Okay, so before we can crank up the heat, we've got to lay down the ground rules. And in the world of thermodynamics, the whole game starts with one really important idea: the pure substance.
So what exactly is a pure substance? Well, the definition is pretty straightforward. It's any material that has the same chemical makeup all the way through, no matter what state it's in: solid, liquid, or gas. Water, H2O, is the classic textbook example. Ice, liquid water, steam, it's all H2O. But here's where it gets a little more interesting. This rule doesn't just apply to single elements or compounds.
Yeah, the really crucial thing here is that chemical consistency. You've got to have the same stuff in every phase. So a glass of ice water, that's a pure substance. Why? Because the ice is H2O and the liquid is H2O. Simple. But what about something like air? Well, if you try to cool down the air around you, you'd find that the different gases in it, like nitrogen and oxygen, they all liquefy at different temperatures. That means the liquid air you'd create would have a totally different chemical composition than the gaseous air still left. So air is not a pure substance.
All right, rules established. Let's get to the fun part. We're going to start the journey. We're taking some regular old room temperature water and we're going to add heat at a constant pressure, just like you would on your kitchen stove. So, what we see is our water's journey playing out in 5 distinct acts. First, at, say, 20 degrees Celsius, it's what we call a compressed liquid. It's stable, it's calm, it's nowhere near boiling. Then, as we crank up the heat and it hits 100 degrees, it reaches this critical tipping point. It's now a saturated liquid. Basically, it's on the very edge, ready to turn into vapor at any second. Add just a little more heat, and boom, we enter the saturated mixture phase. This is the boil. It's a chaotic mix of bubbling water and rising steam. Once every last drop has finally made the jump to steam, we're left with a saturated vapor. But what if we keep going? What if we still keep adding heat? Well, that vapor just gets hotter and hotter, becoming what we call superheated.
And you know, this whole process brings us to what is, for me, the most mind-bending part of this whole thing. Think about it. You can have your stove cranked to the absolute max, but if you stick a thermometer in that pot of boiling water, the temperature won't go up. Not one bit. It's totally, completely stuck.
It's true. So where is all that heat energy going? If it's not making the water hotter, what is it doing? Well, it's being used for one specific job: breaking the bonds that hold those water molecules together as a liquid. This energy has a name. It's called the latent heat of vaporization. And the temperature is just locked in at 100 degrees Celsius until that job is totally done, until every molecule has changed phase.
Okay, so how do scientists and engineers keep track of all this? Let's take a look at how they visualize all these different states on a single, really elegant map. This map lets us see exactly what happens when we start changing other things, like pressure.
And here it is. This is called a TV diagram. It plots temperature on the vertical, up and down axis, against something called specific volume on the horizontal axis. Don't let specific volume throw you off. It's just the volume per unit of mass. Think of this whole thing as a map that lets us trace the entire path of our water molecule. Now, the first thing you probably notice is that big dome shape in the middle. You can think of that dome as the key to the whole map. Everything to the left of the dome, that's our stable, compressed liquid. Everything way over to the right, that's our superheated vapor. And all the action happening inside the dome, that's the boiling zone. That's the saturated mixture where liquid and vapor are hanging out together. The edges of this dome, those lines, they represent the exact tipping points between these states.
Okay, now look at the very top of that dome, that peak. That's a special place called the critical point. If you get water under insane amounts of pressure, we're talking over 22 megapascals, and you get it super hot, something really weird happens. The difference between liquid and vapor, it just vanishes. It's gone. There's no boiling, there's just this one single thing called a supercritical fluid that just gets less and less dense as you heat it up. Wild, right?
So why should you care about this weird map? Why does it matter? Well, because it perfectly explains things that happen in our everyday lives. For example, it explains why it takes longer to cook pasta if you're up in the mountains.
The rule is actually super simple. For any pure substance, its boiling temperature, the saturation temperature, is directly tied to the pressure around it. They are completely dependent on each other. You tell me the pressure, and I can tell you the exact temperature where that substance will boil. It's a lock.
And this chart shows you exactly how that plays out in the real world. You see, down at sea level, we're all used to water boiling at 100 degrees Celsius. But what if you go on a ski trip? Go up to, say, 2,000 meters, about 6,500 feet. The atmospheric pressure is a lot lower. And because of that, water boils at just 93.3 degrees. That's why your pasta or your hard-boiled eggs take forever to cook in Denver. The water just isn't as hot.
And this is exactly what a pressure cooker does. It's basically weaponizing this principle to save you time. By trapping all that steam, it cranks up the pressure inside the pot. I mean, way up. And this forces the boiling point of the water to go much higher, often over 130 degrees Celsius. And hotter water means your food cooks way, way faster. It's just thermodynamics in your kitchen.
But this map can show us even weirder stuff. It can reveal some truly exotic states of matter that only exist under very, very specific conditions.
So get this. There's a place called the triple point. If you get the temperature and pressure just right, we're talking almost a perfect vacuum and a temperature of 0.01 degrees Celsius, something incredible happens. Solid ice, liquid water, and water vapor can all exist at the exact same time, in the same container, in perfect harmony. They're just all there, coexisting.
So what if you drop the pressure even lower, below that triple point? Well, in that case, the liquid phase becomes totally impossible. It just can't exist. Instead, a substance will go straight from a solid to a gas. We call that sublimation. The perfect example is dry ice. The reason dry ice smokes instead of melting is because its triple point pressure is way higher than our normal atmospheric pressure. So at room pressure, it just skips the liquid phase entirely and goes straight to gas.
So think about where we've been. We started with a simple pot of water on a stove, and we've traveled through states of matter we can't even see with our own eyes. We've seen how energy can sort of hide as latent heat, how changing the pressure can completely change your cooking time, and how, at the most extreme points, the familiar lines between solid, liquid, and gas can blur, or even disappear completely. It really makes you wonder, doesn't it? What would it even look like to watch a liquid become a gas with no bubbles, no boiling, just this seamless, almost ghostly transition? The simple act of boiling water really does connect us to some of the deepest rules of the universe.